I'm picking up good vibrations.
Let us now look at some more interesting examples. First, we're going to look at a moving average, which is still a very basic example. But then we're going to look at examples for which the signals are not necessarily 0 for negative n and do not necessarily have a bounded support. Suppose that we want to take a moving average of the input signal depicted here, and the window of this moving average is 3, so that the output will be the average between the current value of the input at time n and the two previous values of the input. Of course, it is trivial, and you can do it without using convolution, but let us use convolution to see how it allows us to arrive at the correct result. First, we need to compute the impulse response of the system, h of n. And this can be done very easily by checking the output when the input is a delta function. So I'm just going to replace here x by delta, and we get that y, or h, because it's the output when the input is an impulse, h is equal to 1 over 3 delta n plus delta n minus 1 plus delta l minus 2, which is also plotted here. So let's follow the steps of the procedure. We start by reflecting h about the signal axis to give h of minus k, and shifting the impulse response to the right, considering h of 1 minus k, h of 2 minus k, etc. We then multiply these shifted versions of the impulse response by the input signal and add the result. This is illustrated here for n equals 2. We multiply by 1/3 the values of the input at time 0, 1, and 2, and then add, which of course gives the weighted average that we want at time n equals 2. So it is great to know that this complicated procedure, convolution, matches what we could do very simply just by computing the moving average. But this procedure will of course enable us to compute other convolutions which would be hard to compute without this procedure. Let us look now at yet another example which is still trivial, but as opposed to the previous one corresponds to a non-causal operation. Suppose that we want to take a weighted average of the input signal by weighting the current value at time n of the signal by 1/2, the future value at n plus 1 by 1/3, and the previous value at n minus 1 by 1/6. The procedure to compute the impulse response is again the same. We just replace x by delta. The resulting impulse response is plotted here, and note that it is no longer 0 for negative n. This is the first time that we encounter signals that are not 0 for negative time. The procedure to compute the convolution is exactly the same, and in particular, we first reflect the signal about the signal axis. However, instead of considering h of n minus k for n equals 0, n equals 1, etc., we also consider negative values of n, and we have to understand when to start. Now, if we shift h to the left by 1 time unit, so corresponding to n equals 1, then we still get a non-zero value signal after we multiply h of minus 1 minus k by the input signal x of k. But if we were to shift the impulse response h of k by 2 time units, so considering h of minus 2 minus k, when we take the product with x of k, we get a 0 signal. So we know now where to start. We should start at n equals minus 1. After considering all these shifted values, we multiply these versions by the input signal, and we add and we get the final result y of n. For instance, for n equals 1, the output is 1 over 2 times the value of the input at n equals 1 plus 1 over 3 times the value of the input at 2 plus 1 over 6 times the value of the input at 0, which is the desired non-causal moving average. Let us now look at another example where both signals are exponentials that start at 0 and go all the way to infinity. This is the first time that we face signals which are not 0 outside of a bounded interval, since both input and output signals are exponential functions for non-negative times and 0 for negative times. So this convolution, we're going to compute it analytically. So here's the formula. Y of n equals summation from k equals 0 until n of x of k times h of n minus k. In the interval between 0 and n, we have that x of k is 0.6 k, and h of n minus k is 0.8 n minus k, which is also equal to 0.8 n times 0.8 to the power of minus n. Okay. So I'm simply going to replace this here, and I get summation from k equals 0 till n of 0.6 to the power of k times 0.8 to the power of n times 0.8 to the power of minus k. So this term here does not depend on k, so we can take it out of the summation. That's because we have a constant multiplying several terms, and that constant we can just group all those terms and multiply by the constant. So basically we get 0.8 power of n times the summation from k equals 0 of the remaining terms, and I can group these two and write them as 0.6 over 0.8 to the power of k. Now we notice that this is a sum of a geometric series, and we have a formula for that. I can write it here. The sum from k equals 0 until n of alpha to the power of k is 1 minus alpha to the power of n plus 1 over 1 minus alpha. So basically we end up with 0.8 n times 1 minus 0.6 over 0.8 to the power of n plus 1 over 1 minus 0.6 over 0.8. So this is a function of n, and this is the function that we were looking for. We're done. I just want to highlight that you can confirm the first values here. You can confirm them, n equals 0, n equals 1, n equals 2, by doing convolution as usual. You should definitely get the same as in this formula here.